Okay, my amazing AP Chem students. So, we are on Unit 8. It's everything to do with acids and bases, pH, all that stuff. And in this video, we're covering topics 8.1 through 8.3. Right? Now, actually, sorry, 8.1 and 8.2 is all. So please turn to page 5 and follow along with me. We're primarily talking about strong acids and strong bases today. But these equations will always work as long as you have concentration of hydronium or hydroxide. Okay, so all of these equations are reliant on that. Now, what's cool is that we use each of these equations and we're going to be calculating with them, but there's relationships between them. So if you are given the pH, you can solve for pOH. And if you're given the pH, you can solve for the concentration of hydronium, H3O+. Now, before I continue, I'll show you an example of this in just a moment, but reminder that H+, these H+ ions can be used, can be exchanged for hydronium, meaning like H+, the concentration of H+ is always equal to the concentration of H3O+. That if something says, an equation says H3O+, you can change it to H+, and if an equation says just H+, you can change it to H3O+. The reason why is if you get H+ in a reaction and there's like a solution, it's with water, then it's going to react and make this H3O+. And again, the name of this is hydronium, H3O+. All right, great. So often you're going to be looking at this, you're going to look at questions, and you're going to say, hey, it gave me this. Like, I have this, and I need to get to the concentration of hydroxide. Well, guess what? We have two pathways. We could take this pathway where we use this equation, or we can go from concentration of our hydronium to our pH, and from our pH we can figure out our pOH, and then from the pOH we can get to hydroxide. So one path is sometimes shorter than the other path. So knowing these relationships can be very helpful. Let me talk through each of these, and then I want to show you where they're at on your reference guide. So let's start with just the equation for pH. So pH is equal to the negative log of the concentration of hydronium, or the concentration of H+. Well, guess what? If you add a P in front of anything, this means negative log. Okay, so if there's a P and then an H, then it's the negative log of H, of the concentration of H+. So pH is equal to the negative log of H+, and again, we can replace that with hydronium, H3O+. This is a log base 10, by the way. So if you have a log base 10, this equation can be rearranged. Instead of solving for pH, you can solve for the concentration. And so what you do is, right here, the concentration of H+ will equal 10 raised to the negative of the pH. And so that's how you can go back and forth between these. So if you are given concentration and you're solving for pH, then you do negative log of that concentration. That will give you the pH. On the other side of this, if you are given pH, you can solve for the concentration by doing 10 raised to the negative pH, and that will tell you the concentration. So if it's a pOH, it's the same idea, but instead of the negative log, because remember that's what the P is, instead of the negative log of H, it's the negative log of OH, of our hydroxide. And then we get the similar rearrangement here, that the concentration of hydroxide is equal to 10 raised to the negative pOH. All right, so you're going to be using those equations quite a bit. The other cool thing is that if you take pH and you add it to pOH, so the pH plus POH always equals 14. So if I'm solving for either of these, like let's say I'm solving for pH, well, I would just subtract POH. 14 minus POH equals pH. Or if I was solving for POH, 14 minus pH would equal the POH. So that's what we see right here. And then the last one is this KW. I'm going to explain more in a moment what KW is, but this is the value that it's equal to. And if you multiply together the concentration of hydronium multiplied by the concentration of hydroxide, that equals 1 times by 10 to the negative 14. Now, something I need to clarify, all of these, this is conditional upon temperature. This is true at 25 degrees Celsius. Okay? That this only works at 25 degrees Celsius, this only works at 25 degrees Celsius. I think these ones are fine without it, but definitely those ones are only 25 degrees Celsius. If they do not tell you the temperature, you can assume that it's 25 degrees Celsius. Okay, beautiful. Where are these at on your reference guide? So, on our blue reference sheet, there's a part that says equilibrium. So, first thing, I need you to see how they tell us, oh, come on, I hit the focus button, it did the opposite of focusing. It tells us pH is equal to the negative log of hydronium. So it said pH is equal to the negative log of this hydronium. So they give us this equation, but notice what they do not give us, the rearrangement of that equation. So you are provided this, but you need to know that 10 raised to the negative pH will tell you the concentration. That's also true with the POH. They tell you POH is equal to the negative log of hydroxide, but they do not tell you on your reference guide that 10 raised to the negative POH is equal to the concentration of hydroxide. They also tell you that if you take pH plus POH, that it equals 14. So that's given to you. Notice how it says at 25 degrees Celsius. And then it also tells you the bottom equation, that if you multiply the concentration of hydronium times by the concentration of hydroxide, that it equals 1 times by 10 to the negative 14. So all of these equations are found on your reference guide. It's just a matter of knowing where they are. All right, what is KW? Something called the self-ionization of water. Let's say that I have 2 water molecules, 2 H2O, and the picture here is helpful. So see my 2 water molecules? What if I break this hydrogen off and I give it to this water molecule? That would turn that one into hydronium, an H3O+, and then it would turn this one into hydroxide, an OH-. Right? Now what's cool about this is no matter how many of these water molecules I break apart, it will always result in equal amounts of hydronium and hydroxide. So if 2 of these break apart, I get 1 hydronium and 1 hydroxide. If 20 of these break apart, I get 10 hydronium and 10 hydroxide. So it will always be the same. Everyone, when it is water, not a solution, not water mixed up with something, if we are talking about pure water, the concentration of hydronium is always equal to the concentration of hydroxide. Okay? No matter the temperature, this is really important. They love asking you questions about this, and they're like, if this gets bigger, what happens to this? Well, it would also get bigger. They have to always be equal to each other. Okay? All right, next thing. What if it was only 1 water molecule? Same idea, H2O. Well, guess what? If we have this H2O and a hydrogen breaks off of it, and H+ breaks off of it, you're left with a hydroxide. Oh my goodness, see what I was telling you before? How hydronium can be replaced with hydrogen with H+. So again, they can always be exchanged. If you're given hydronium, you can replace it with H+ or vice versa. Okay, now if this is my reaction, and this is like liquid, and these are aqueous ions, right? These ions are broken apart and they're floating in water. We could write a K expression for this. Reminder, K expressions are products divided by reactants, but if something is a solid or a liquid, then they're not part of the K expression. So here's my products. So I could have hydronium, or H+, multiplied by the concentration of hydroxide. I would not have this part. I wouldn't have divided by water liquid because it's a liquid. And that's going to be the Kw. Kw is equal to that expression. Well, we did some testing at 25 degrees Celsius, and we found that the K value for water, that's what the W stands for, is equal to 1 times by 10 to the negative 14. All right, great. Reminder, that's provided for you. The concentration of hydronium times by hydroxide is equal to 1 times by 10 to the negative 14. You don't have to memorize it, but it is a really useful bit of information. So it says here, the concentration of hydroxide in a solution is found to be this. So the concentration of hydroxide is 1.4 times 10 to the negative 11 at 25 degrees Celsius. Find the concentration of the hydronium. Okay, now notice they said solution, not pure water. Okay, so everyone, if they had said the concentration of hydroxide in water is found to be this amount, then the concentration of the hydronium would just be equal to it. They'd be exactly the same value. Okay, but it's not, it's a solution. But what's really cool is that this relationship still works. Meaning if I multiply these together, then it will equal 1 times by 10 to the negative 14. We were given hydroxide, and we're solving for hydronium, and we're going to use this relationship to find that. I'm just going to write the number down. So the Kw is equal to 1.0 times 10 to the negative 14. So Kw is equal to concentration of hydronium multiplied by concentration of hydroxide. If I'm solving for hydronium, I would divide by the concentration of hydroxide. So Kw divided by that concentration of hydroxide. This will equal the concentration of H3O+. All right, so my Kw, 1 times by 10 raised to the negative 14 divided by the concentration of the hydroxide, 1.4 times by 10 raised to the negative 11. We're dealing with 2 sig figs right now. So then my final answer would be 7.1 times by 10 to the negative 4. And this is a concentration, so units are capital M molarity, molar. Nice. Okay, next. So, an acid. We know from a prior unit that acids are hydrogen donors, that they lose a H+. They're proton donors. They lose an H+. So, this is my acid, same here. If the acid loses the hydrogen to the water, then the water becomes hydronium, and we're left with an A-. Okay? So if the H+ is given to the water, then we're left with an A-. Just a reminder that this is a conjugate as well. So if this is the acid, acids lose a hydrogen, then this is its conjugate base. and that we have water that's going to gain a hydrogen. That's what makes it a base. And this is its conjugate acid. Okay. Now, you can also just say, you can use either of these when it comes to doing calculations here in a little bit. But an acid, it just loses the hydrogen, right? The hydrogen, it ionizes, it breaks off of it. They break apart into ions. And so then this would break apart into H plus and A minus. All right. What I need you to know is that strong acids more or less completely ionize. So that would mean that every or practically every molecule of the acid would break apart into H plus and A minus. Okay, more on that in a moment. Find the pH of pure water at 25 degrees Celsius. Okay, well, let's think about this for a minute. We know a couple of things. We know that the concentration of hydronium multiplied by the concentration of hydroxide is equal to 1 times by 10 to the negative 14. Yeah. And then if it's pure water, the concentration of hydronium is equal to the concentration of hydroxide. Okay, that these are the same numbers. So instead of saying hydronium multiplied by hydroxide, couldn't I do the concentration of hydroxide squared? Like this is equal to that, and then two things that are equal to each other that are multiplied, right? It's squared, and that would equal 1 times by 10 to the negative 14. Okay, what if I want this concentration? I would take the square root of both sides. So square root here and square root there. So then the concentration of H3O plus would equal the square root of our value here, of our Kw. So 1.0 times by 10 raised to the negative 14. And we're going to take the square root of that. This equals 1 times by 10 to the negative 7. Now, it didn't ask what was the concentration of the hydronium. It asked what the pH was. And we know, I have this printed on the back of your packet as well. We know that if we take the negative log of this hydronium, then we're going to get the pH. Like we have this right now, the concentration of hydronium, and we're solving for pH. It's a log base 10. So if you've worked with logs before, you might be able to do this without a calculator. This base 10, if it's 1 times by 10 raised to something, and you do the negative log of this, then you make that positive and it equals 7. But let's run in the calculator just to show you. So I'm going to take the negative log, here's my log button right there, of 1 times by 10 to the negative 7. Close that parentheses. This is equal to 7 times by 10 to the 0. Anything raised to the 0 is 1, so it's 7 times by 1, which is 7. So the pH is equal to 7. Now this makes sense though, let's think about it. Because it's water. Water has a pH of 7, it's neutral. And the reason why it's neutral, people, is because the concentration of hydronium is equal to the concentration of hydroxide. That the acid part and the base part, they're equal to each other. That's what makes it neutral. Okay, now, we'll practice this as a class. When you come down here, I'm going to show you a couple things. First off, at any point in here, like we were just at 7, we know the pH is 7, look at the pOH is 7. Oh, and we saw this. We saw that if you take the pH we saw that if you take the pH and you add it to the POH, that you're always going to get 14. And this happens every single time. 4 plus 10, 14. 12 plus 2, 14. Okay? But a couple important things to remember. The lower the pH, the more acidic something is, and what makes it more acidic is the fact that it has more of the H plus or more of the H3O plus. The higher the pH, the more basic something is, and it has less H plus in it. It also has more of the hydroxide in it. Okay? So if I'm coming down here, this is going to be my H plus or my H3O plus. And then this is going to be the OH minus. And so I have my concentrations here. And look at this. If I have equal amounts, so like equal amounts of hydroxide and equal amounts of hydronium, or the H plus, sorry I didn't draw that quite in the middle, that's when it's neutral, like water. That's when it's a pH of 7. If we lower our pH, we become more acidic because we have more H plus in there. If we raise our pH, we have a higher pH that's more basic, and there's more hydroxide and less H plus. So that was our pH. Okay, down here, what about POH? Well, pH plus POH is equal to 7, right? So 0 plus 14 would equal 14. 14 plus 0. So we have this opposite relationship here, that as pH increases, POH decreases, and vice versa. So just keep that in mind. And last thing, label this for me. This is the acid side. This is our acidic side. This is the basic side there. Okay, back to what I was telling you before. These are the strong acids. You need to have these memorized. You need to know as soon as you see one of these that it is a strong acid. That means that whatever the concentration is of any of these strong acids, it is equal to the concentration of H plus, or equal to the concentration of hydronium, because they all completely dissociate. Every single one of these hydrogens bonded to the chlorines in a solution, they actually break apart, so all of them are actually H pluses. HCl turns into H plus and Cl minus, right? So however many of these you have, it's actually the same amount of this and this, so they all broke apart. Okay. Find the pH of 0.0205 molar HCl. First you recognize this is a strong acid. And if that's a strong acid, then the concentration of that strong acid is equal to the concentration of H plus, and that's 0.025 molarity. Now, we're solving for the pH. I have my H plus and I'm solving for my pH. So I'm going to take the negative log of this concentration, and that's going to equal my pH. So I'm going to do the negative log of this concentration, and that is going to equal pH. Negative log of 0.025. Okay, we have 1.60206. Okay, now I'm putting a lot of digits because I need to talk to you guys about sig figs. Sig figs are really, really weird with log values. So this is what I need you to know. The leading digit on a pH value is not significant. I know, that's so crazy. Any P value, POH, pH, pKa, anything that starts with P, the first digit is not significant. So that means that our concentration was 2 sig figs, so our answer has to be 2 sig figs. So my final answer is 1.60. Okay. Now, if you want to know why it's not significant, come talk to me. It's when this is in scientific notation, it's actually the same as it's a raised to number. It's really weird, but for anyone that's interested, I'll give you more info. Just know that the leading digit for a pH value is not significant. We still include it, but it's not significant. Alrighty. How much time do I have? Got 5 more minutes. Okay. The concentration of H2SO4. All right, this is what I need you to know. If it's polyprotic, that means that there's more than one hydrogen here. Then we got to account for this. So let me just double check something. So sometimes it only loses one proton, one H plus, and I don't want to tell you this wrong, so I just want to double check if it loses both of those hydrogens or if it only loses one of them. I think it's only one of them. Okay. I will do some diving to double check, but I'm fairly certain right now. Let's see. Ooh, conflicting answers, dang it. All right, JK, I'm going to come back to this. I'm going to do a little research, and then we'll do this one together as a class. So either only one of the hydrogens break off or both of the hydrogens break off, and then that will tell us concentration. So let's keep going. POH, we can do easy enough. We're not going to do example 7. Example 7 is exactly the same as example 2 because the concentration of hydronium is equal to the concentration of hydroxide in pure water. And so guess what? If that's the concentration of the hydronium, then that's equal to the concentration of the hydroxide. 1 times by 10 to the negative 7 molarity. Great. Strong bases. So reminder that strong bases contain a group 1 or a group 2, most of the group 2. Like you can pretty much just assume all of group 2. So a group 1 or a group 2 metal plus hydroxide. Okay. So for this first one, find the POH of 0.015 molar KOH. So I have a group 1 and I have a hydroxide. This is a strong base. Just like our strong acids, whatever the concentration is of that strong base, it's the same. It equals the concentration of the hydroxide. So we have concentration of hydroxide and we want POH. Well, reminder, P just means negative log and then this concentration of hydroxide. So we know that the concentration is 0.015 molarity. So if I do the negative log of that 0.015, then that would equal, without sig figs, 1.8239. pHs and POHs are unitless, but what would the sig figs be? So just a reminder, anytime it's a P value, a pH, a POH, etc., the leading digit is not significant. So we had 2 sig figs before, and so we need 2 sig figs. So my final answer for POH is 1.82. All right. Last thing. Sometimes we're not at 25 degrees Celsius, especially when it comes to water. And so I need you to know that when the temperature is higher for water, we get a greater amount of hydronium and hydroxide, but if the temperature is less than 25, then we get a lower concentration of hydronium and hydroxide. But what is always true, it doesn't matter the temperature, that the concentration of hydronium is equal to the concentration of hydroxide. This is always true when it's pure water. Okay, more on that later in class. We'll cover this like self-ionization of water bit, and then we'll get some practice in. All right, everyone, thank you for your hard work.